There are moments in your life where you realize you've made a terrible mistake. For me, that moment came when I walked into a physics seminar room at Princeton and saw Albert Einstein sitting in the front row. I was 21, a graduate student. I'd been at Princeton for less than a year, and I was about to tell the man who discovered relativity that the way we understood electrons might be completely wrong. The year was 1940. The world was at war, though America hadn't joined yet. Europe was burning. But in this quiet room at Princeton, none of that mattered. What mattered was physics. What mattered was truth. Let me tell you what led me here. I didn't come from the world of physics royalty. I came from Far Rockaway, a little beach town at the edge of New York. My father wasn't a professor or a scientist. He sold uniforms, but he understood something important about learning. He taught me that knowing something and understanding something are completely different. I remember walking with him as a kid. I'd point at things and ask what they were called. He'd tell me the name, then he'd say, "But that doesn't tell you anything about what it actually is. That's just what people decided to call it." He was teaching me to look past the surface, to ask how things really work, not just what they're labeled. That curiosity became an obsession. By the time I was a teenager, I'd turned my bedroom into a laboratory. I'd fix radios for money, not because I needed to learn the technical steps, I could figure those out, but because I wanted to understand why the circuits worked the way they did, what was actually happening when electricity moved through a wire. I went to MIT, graduated in 1939. Then I took the graduate entrance exam for Princeton and scored a perfect on the physics portion, the first person to ever do that. But here's what a perfect test score doesn't prepare you for: standing in a room with the people who wrote the rules you were tested on. Princeton in 1939 was a strange place. Beautiful campus, old stone buildings, leaves changing colors. But underneath that peaceful surface, there was this incredible intellectual tension. The Institute for Advanced Study was right there. Einstein worked there. Von Neumann worked there. The people who were literally inventing modern physics were walking the same paths I was. I'd see Einstein sometimes. He'd be shuffling along in this old sweater, hair completely unkempt, looking like he'd just rolled out of bed. But his eyes, when you caught his eyes, you could see he was somewhere else entirely, thinking about something none of us could touch. This was the man who had changed everything. 20 years earlier, he'd published his general theory of relativity. He'd shown that what we call gravity isn't a force at all. It's the shape of space-time itself. Mass bends space and time, and objects move along those curves. The Earth doesn't orbit the sun because it's being pulled. It orbits because the sun creates a valley in space-time, and the Earth is rolling along the edge of that valley. It was beautiful. It was complete. It was revolutionary. And I was about to suggest it might be missing something. I'd started working with John Wheeler. He was young for a professor, only in his late 20s, but he was brilliant. More importantly, he was willing to entertain ideas that sounded crazy. We'd been working on a problem that had bothered me since I first learned quantum mechanics. It was about electrons and radiation. Here's the situation. When you accelerate a charged particle, an electron say, it gives off electromagnetic radiation, light, radio waves, whatever. We've known this for decades. Maxwell's equations predict it. Experiments confirm it. But there's something weird about it. When the electron radiates, it loses energy. That energy goes into the electromagnetic wave that's traveling away from the electron, and the electron recoils. It kicks back like a gun when you fire it. Except here's the puzzle. Why does it recoil? With a gun, you can explain it. The bullet goes forward, the gun goes backward. Conservation of momentum. Simple. But with an electron, the radiation is traveling away into the future. It hasn't hit anything yet. It's just propagating outward at the speed of light. So what is the electron recoiling against? The standard answer was self-interaction. The electron creates an electromagnetic field. That field exerts a force back on the electron itself. The electron feels its own field, and that's what causes the recoil. Fine. Mathematically, you can write that down. But when you actually try to calculate it, you run into a disaster. The equations give you infinity. Not as a metaphor, literally infinity. The energy of the electron comes out infinite. The mass comes out infinite. Everything blows up. Physicists had developed tricks to deal with this. You'd calculate one infinity, calculate another infinity, subtract them, and get a finite answer. It worked. The predictions matched experiments, but it felt wrong. It felt like we were papering over something we didn't understand. Wheeler and I had a different idea. What if the electron doesn't interact with itself at all? What if the reason it recoils is because of all the other charged particles in the universe? Here's how it works. The electron sends out a wave into the future. That wave hits other electrons, other protons, everything with charge in the entire universe. Those particles absorb the wave and respond by sending out their own waves. And here's the key part. Some of those response waves travel backward in time. They arrive at the original electron at the exact moment it started radiating. And it's those backward traveling waves that cause the recoil. No self-interaction, no infinities, just electrons talking to each other across time. It sounds insane. Waves traveling backward in time, signals from the future. But the math worked. We called it the absorber theory. Wheeler loved it. He kept pushing me to develop it further, to check every corner of it, to make sure it was really consistent. And then he said I should present it at a seminar. I didn't know who was coming until the day of. Wheeler had organized it. He'd invited people. I assumed it would be graduate students, maybe a few professors. Then Wigner told me Einstein would be there. My stomach dropped. Einstein, Pauli, von Neumann, Wagner himself, Henry Norris Russell, the astrophysicist, all of them in one room, listening to me. I wanted to run. I genuinely considered just not showing up. But Wheeler had put his name on this theory too. I couldn't embarrass him. The morning of the seminar, I could barely hold my chalk. I was at the blackboard early, writing out the key equations, trying to calm myself down. My handwriting was shaky. I kept dropping the chalk. Then they started arriving. Von Neumann came in, nodded at me politely. Then Pauli. He had this look on his face like he was already preparing to tear me apart. Then others filed in, taking their seats. And then Einstein walked in. He didn't sit in the back. He sat in the front row, right in the center. He looked up at me and smiled, just a gentle, encouraging smile, like he was there to learn something. I wanted to die. I started talking. I don't remember my exact words. I know I explained the problem first, the infinities, the self-interaction issue, the fact that our current understanding was mathematically ugly. Then I explained our solution, electrons interacting with all the other charges in the universe, waves traveling forward and backward in time, the idea that what we call radiation reaction is actually a response from the future. As I talked, I kept glancing at Einstein. He was completely focused, leaning forward slightly, following every equation. He didn't look skeptical. He looked curious. I went through the mathematics. I showed that it gave the same predictions as the standard theory. I showed that the infinities canceled out. I addressed the obvious objection. Yes, this requires accepting that electromagnetic waves can travel backward in time, but that's not actually forbidden by Maxwell's equations. When I finished, there was silence. Then Pauli spoke up. I don't think this can be correct, he said. His accent was thick, his tone sharp. Because of this problem and this problem and this other problem. I started to respond, but Pauli cut me off. He turned to Einstein. Professor Einstein, surely you agree. This was it. Pauli was asking Einstein to kill my theory. The great Wolfgang Pauli, who'd won the Nobel Prize, who was famous for being able to destroy a theory with a single sentence. And he was asking Einstein to back him up. Einstein was quiet for a moment, and then he said very slowly, "No." The whole room shifted. Everyone turned to look at him. I think the problem is not with the theory itself, Einstein said. The problem is that it would be very difficult to generalize this to gravitational interactions. He paused. Then he said something I've never forgotten. But general relativity is not as firmly established as electrodynamics. I wouldn't use that as an argument against the theory. Maybe we need a new approach to gravity as well. Do you understand what had just happened? Einstein, the Einstein, had just said that maybe his own theory of general relativity needed to be rethought. And he'd said it to defend a 21-year-old graduate student's wild idea about electrons talking to each other through time. The absorber theory never became mainstream. Pauli was probably right about some of his objections. The theory had problems we couldn't fully resolve. It made correct predictions, but it was too strange, too philosophically difficult for most physicists to accept. But that's not what mattered. What mattered was that Einstein took me seriously. He didn't dismiss me because I was young. He didn't reject the idea because it was strange. He engaged with it. He thought about it. He protected it. That's what a real scientist does. Years later, when I was working on quantum electrodynamics, when I was developing the path integral formulation and Feynman diagrams, I thought about that day constantly. I thought about Einstein's willingness to question his own work, his willingness to say perhaps instead of no. I learned more from that one word, no, drawn out in his German accent, than from any equation. I learned that being a scientist means staying curious even when you're famous. It means listening even when you've already won the Nobel Prize. It means defending new ideas even when they challenge your own. Einstein could have sided with Pauli. It would have been easy. It would have been safe. But he didn't. He said perhaps. And that made all the difference. I was Richard Feynman, and I was just getting started.